Modules and Homological Algebra, Lecture 9. Principal Ideal Domains. Let us start by recalling what a commutative domain is. Let R be a commutative ring. Please note that we always assume that our rings are unital. So our ring R has a unit. Recall that a ring R is called a domain provided that multiplying two non-zero elements of R, we necessarily get a non-zero element. So R is a domain if it does not have non-trivial zero divisors. Principal examples of domains are: any field is a domain, the ring of integers is a domain, the ring of polynomials in one or more variables over some field K is a domain. A negative example is the ring which we obtain if we take a field K and take a direct sum of this field with itself. Please also note that fields are very easy examples of commutative rings. The theory, which we will develop in this part of the course, will be mainly oriented on those commutative rings that are not fields. Now we can define our main protagonist, principal ideal domains. Recall that an ideal I of a ring R is a non-empty subset of R, which is stable under addition of its elements and under multiplication with elements in R. Since we assume that R is a commutative ring, it doesn't matter from which side we multiply. In particular, any ideal of R contains 0. This is because multiplying an element in the ideal with 0, we will get 0, and this should be an element in the ideal. Two easy examples. The element 0 itself forms an ideal in any ring R, and the whole ring R is obviously an ideal of R. Here is a more typical example. Given some element x in R, we have the principal ideal generated by x, and it consists of all elements Rx, where R is an element in R. Definition: a domain R is called a principal ideal domain, provided that any ideal in R is principal. Here are two classical examples. Both the ring of integers and the ring of all polynomials in one variable over some field K are principal ideal domains. We will discuss the proofs on the next slides. And here's a negative example. The ring of polynomials in two or more variables over a field K is a domain, but it's not a principal ideal domain. For example, for the case of two variables, the ideal generated by the variables, by x and y, is not a principal ideal. It is not generated by one element. So let's show that the ring of integers is a principal ideal domain. So let I be an ideal in Z. So if I is a zero ideal, then of course it is generated by the element 0, so it's a principal ideal. If it is not a zero ideal, it contains a non-zero element A, and hence also minus A, because minus A is minus 1 times A. And therefore our ideal contains a positive integer. Let A be the minimum positive integer contained in this ideal. So we claim that our ideal I coincides with the principal ideal generated by the element A. Indeed, let B be an element in I. Then we can write B as A times something plus the rest. So here something, we denoted by K, is just an integer, and the rest is an element between 0 and A minus 1. So we divide B by A with the rest R. In particular, we can write that our rest R is equal to B minus AK. Since B is in the ideal and A is in the ideal, this element belongs to I. But we assume that A is a minimal positive element which belongs to I, so R must be equal to 0. In other words, B is divisible by A. And this means that B belongs to the principal ideal generated by A. Now let us similarly show that the ring of all polynomials in one variable over a field K is a principal ideal domain. Let I be an ideal in this polynomial ring. If I is 0, then it's the principal ideal generated by 0. If I is not 0, then it contains a non-zero polynomial, and let f of x be a non-zero polynomial in the ideal I, which has minimal possible degree. We claim that I is the principal ideal generated by f of x. Indeed, given a polynomial g of x in I, we can divide g of x by f of x with the rest r of x, and here the rest r of x has degree which is strictly smaller than the degree of f of x. Again, we write the rest as g minus f times our quotient h, and this belongs to our ideal I. By our choice of x, it's a polynomial of minimal degree in our ideal, we conclude that the rest should be 0, or in other words, g is divisible by f. So it belongs to the principal ideal generated by f. Now let us discuss prime and irreducible elements in commutative rings. Let R be a commutative domain. Recall that a non-zero and non-invertible element R in R is called prime, provided that it has the following property. If it divides the product AB of any two elements in R, then it must either divide A or B. And this element R is called irreducible, provided that as soon as we write R as a product of two elements A and B, it should follow that either A or B is an invertible element. For example, prime integers are both prime and irreducible elements in the ring of integers. Example 2, polynomials of degree 1 are both prime and irreducible elements in the ring of all polynomials in one variable. An interesting observation is that each prime element is irreducible. Indeed, if R is a prime element and we write R as the product of A and B, then since R is prime, R should divide A or B. So let's assume that R divides A. Then we can write A as R times something, or in other words, if we now insert it into the equation R is equal to AB, we get that R is equal to R something times B. So we denote the something by X, and now we move everything to the left-hand side and take R out, and we get the equation R times 1 minus XB is equal to 0. Since R is a domain and our element little r is non-zero, we assume that it is prime, so it's not 0. It follows that 1 minus xb should be 0. In other words, 1 should be equal to xb. And this means that b is invertible and completes the proof of our statement. Now we can discuss the notion of a unique factorization domain. Let R be a commutative domain. Definition: a factorization of a non-zero element R in R into irreducible elements is an expression R is equal to A1 times A2 times and so on times AK, where all AI are irreducible. For example, 10 is equal to 2 times 5 is a factorization of an element 10 in the ring of integers into a product of two irreducible elements 2 and 5. They are prime and so irreducible in Z. Definition: two irreducible elements A and B in some ring R are called associated, provided that A is equal to Bx for some invertible element x. So we always assume that R is a commutative domain during this lecture. Example: the elements 2 and minus 2 are associated in the ring of integers. This is because minus 2 is equal to minus 1 times 2, and minus 1 is invertible in Z. Definition: a domain R is called a unique factorization domain, or UFD for short, provided that each non-zero element in R admits a finite factorization into a product of irreducible elements. Moreover, this factorization is unique up to permutation and association. This means that if we have two different factorizations of some element R, One is the factorization r is equal to a1, a2, and so on, ak. And another factorization is r is equal to b1 times b2 times and so on times bm, where all ai's and all bj's are irreducible. Then we must necessarily have that k is equal to m, so the lengths of factorizations are the same, and there should exist a permutation sigma in Sm such that each element ai is associated to the element b sigma of I, for all I. Next, let us discuss the notion of a noetherian ring. Let R be a commutative domain. Definition: R is called noetherian provided that any ascending chain of ideals in R stabilizes. This means that for any chain of ideals in R, so the ideal I1 is included into the ideal I2, is included into the ideal I3, and so on, there should exist a positive integer n such that the chain stabilizes after n steps. So In is actually equal to In plus 1, is equal to In plus 2, and so on. For example, the ring Z of all integers is noetherian. Indeed, take any ascending chain of ideals in Z. So we have ideal I1 embedded into I2 and so on. Let us denote by Km the minimal positive integer which belongs to Im. So we can of course assume that starting from some point these ideals are non-zero, so we just assume that they all are non-zero, so this Km is well defined. Moreover, we already saw that with this choice, the ideal Im is actually the principal ideal generated by Km. And because of the inclusion, we have that K1 is greater than or equal to K2 and so on. And this sequence certainly stabilizes because the integer interval between 0 and K1 contains only finitely many elements. And this means that our sequence of ideals also stabilizes. We can give the following characterization of noetherian rings. A commutative domain R is noetherian if and only if any ideal in R is finitely generated. Proof: assume that any ideal in R is finitely generated. Let I1 included into I2 included and so on be an ascending chain of ideals in R. Then the union of all these ideals is of course an ideal in R, and it is finitely generated by our assumption. So let X be a finite set which generates I. So since X is a finite set, there should exist M greater than 0 such that the whole set X belongs to Im. And then after that M, the chain of ideals obviously stabilizes because all other ideals contain this X. And this shows that R is noetherian. Conversely, let us assume that we have an ideal I which is not finitely generated, and it is generated by an infinite set A1, A2, A3, and so on of elements, but there is no finite set of generators. Then we can consider the sequence of ideals. The principal ideal generated by A1 is included into the ideal generated by A1 and A2, and so on. And by the assumption, this chain never stabilizes, and this means that R is not a noetherian ring. So this gives us this characterization of noetherian rings, and in particular, as a corollary, we get that any principal ideal domain is noetherian. This is because all ideals are generated by one element. They are principal. Now we can prove existence of factorizations in principal ideal domains. Moreover, we even prove more general result for noetherian domains. So let R be a commutative noetherian domain, then any non-zero and non-invertible element in R admits a factorization into a product of irreducible elements. Proof: assume that some element R in R does not have such a factorization, then in particular it's not an irreducible element, and so we can write this element as a product of R1 and R2, where both R1 and R2 are not invertible. Without loss of generality, we may assume that one of them doesn't have any factorization, because if both have factorization, we multiply the factorizations, we get a factorization for R. So let's assume that R1 doesn't have any factorization as above. Then the principal ideal generated by R is included into the principal ideal generated by R1, and this inclusion is proper. Indeed, if these two ideals would coincide, we should be able to write R1 as R times something times some x. And therefore, since R is equal to R1, R2, we can plug in this expression for R1 into this equality, move everything to the left-hand side, and take R out of the bracket to get R times 1 minus x R2 is equal to 0. And this, because we are over the domain, this would mean that 1 is equal to x R2. In other words, R2 is invertible. And this is a contradiction because we assume that R2 is not invertible. So R is a proper ideal in R1. And now we just proceed. We write R1 as Q1, Q2, with both Q1 and Q2 non-invertible. The same argument as before, say that the ideal generated by R1 is properly embedded into the ideal generated by one of these elements, let's say Q1. And so on. Since our R is assumed to be noetherian, an infinite continuation of this process leads to a contradiction. Therefore, this infinite continuation of this process is impossible, so eventually we will end up with an element which has a factorization. In particular, it follows that any non-zero and non-invertible element of a principal ideal domain admits a factorization into a product of irreducible elements. Now let us recall what maximal ideals are. Let R be a commutative domain. Definition: an ideal I in R is maximal, provided that it is different from R, and for any ideal J in R, which contains I, we have that J coincides with I, or J coincides with R. Here is a characterization of maximal ideals. An ideal I is maximal if and only if the quotient of R modulo I is a field. Proof: using one of the isomorphism theorems, if we take an ideal J which contains I and map it to the quotient of J by I, this map is a bijection between the set of all ideals in R which contain I and all ideals in the quotient R modulo I. And therefore, the ideal I is maximal if and only if R modulo I does not have any proper ideals. And this means exactly that R modulo I is a field. For example, for any prime integer p, the principal ideal generated by p in the ring of integers is maximal, and the corresponding quotient is a field with p elements. Second example, for any polynomial f of x of degree 1, the ideal generated by this polynomial in k of x is maximal. So here again k is a field. And the quotient of k of x by this ideal is actually isomorphic to k. Next, let us discuss prime ideals. Let R be a commutative domain. Definition: an ideal I in R is prime, provided that it is different from R, and for any A and B in R, the fact that the product AB belongs to I implies that A belongs to I or B belongs to I. Proposition which characterizes prime ideals: the ideal I is prime if and only if the quotient by this ideal is a domain. Proof: the condition that AB belongs to I implies that A belongs to I or B belongs to I is exactly the condition that in the quotient, the product of the class of A with the class of B is equal to 0, if and only if the class of A is 0 or the class of B is 0. So this gives us our proposition. An immediate corollary is that every maximal ideal is prime, and this is because every field is a domain. An ideal is maximal if the quotient is a field. An ideal is prime if the quotient is a domain. Since any field is a domain, any maximal ideal is prime. For example, in the ring of integers, the principal ideal generated by a prime integer is prime. And example 2, in a polynomial ring, the ideal generated by a polynomial of degree 1 is prime. Now let us prove that in a principal ideal domain, the notions of prime and irreducible elements coincide. So proposition, in any PID, an element is irreducible if and only if it is prime. Proof. Since we know that primes are always irreducible, we only need to show that irreducible elements are prime. Let R be an irreducible element of a principal ideal domain. We claim that the ideal generated by R is maximal, hence prime, and this means that R is a prime element. So assume that we have an ideal I, which contains the principal ideal generated by R, and which is different from the whole ring R. Then I is a principal ideal because R is a principal ideal domain. So let's say that it's generated by some element A. This means that our element little r belongs to the principal ideal generated by A, so it is equal to A times x, for some element x in R. Since R is irreducible and the element A is not invertible, because the principal ideal generated by A is assumed to be different from the whole ring R, it follows that x must be invertible. But then this implies that A is equal to R times X inverse, and so the ideals generated by A and R coincide. And this proves exactly that the ideal generated by R is a maximal ideal. Now we can prove the main theorem that every principal ideal domain is a unique factorization domain. We have already established existence of factorization, so we only need to establish uniqueness. So assume that some element R in our principal ideal domain, which is not zero and not invertible, can be written as a product of irreducible elements in two different ways. We know that all irreducible elements in a principal ideal domain are prime. So all our elements here are prime. So the element A1 is prime, and since A1 divides the product of all B's, it should divide one of these elements. So let's assume that it divides B1. And so we can write B1 as x times A1, but B1 is irreducible, so x must be invertible. And since R is a domain, we can now plug this into the expression, move to the left-hand side and take A1 out. So A1 is a non-invertible element, so this means that this product being equal to 0, the second factor should be 0 because we are in a domain, which means that the product of A2, A3, and so on AK is equal to the product of B2, B3, and so on Bm times our invertible element x. And now we simply complete the proof by induction on the length of a shortest factorization. We already established that A1 is associated to B1, and we took them out of the game, and we proceed by induction. Please note that there exist unique factorization domains that are not principal ideal domains. For example, any polynomial ring in a finite number of elements is actually a unique factorization domain. But if the number of variables is bigger than 1, it's not a principal ideal. Our aim in the coming lectures is to describe finitely generated modules over principal ideal domains. This is our main aim. Due to our principal examples of principal ideal domains, as special cases, we will get classification of all finitely generated abelian groups. These are Z modules. And we have the classification of Jordan normal forms. This is a classification of finitely generated modules over the polynomial algebra in one variable over complex numbers. And it's quite interesting to note that we will see that these two results are special cases of the same result, and they can be proved using the same technique. As another application of the same theorem, we will get classification of finitely generated modules over real polynomials and finitely generated modules over Laurent polynomials. So we start our investigation of modules of rings with the notions of annihilators and torsion. So let R be a commutative ring and M an R module. Let little m be an element in M. Definition: the set of all elements in R which apply to M give 0 is called the annihilator of our element little m. It is very easy to check that the set is an ideal of R. The annihilator of each element in each module is a certain ideal of R. For example, the annihilator of the 0 element is the whole ring R. That's obvious. And the second example, if we take as a module the regular module and as an element the identity element in R, then of course the annihilator of the identity element is 0. Definition: we say that an element M in this module big M is torsion, provided that its annihilator is non-zero. And we will say that the whole module is torsion, provided that every element in this module is torsion. Now we can discuss the notion of a torsion submodule. Proposition: let M be a module over a commutative domain R. Claim: then the set MT of all torsion elements in M is a submodule of M. Proof: let us first note that the 0 element is a torsion element because its annihilator is the whole ring. So in particular, the torsion part is a not empty set. It is non-empty. Let X and Y be two elements in the torsion part, and let A and B be two non-zero elements in our ring R, such that A belongs to the annihilator of X and B belongs to the annihilator of Y. Since R is a domain, the product AB is a non-zero element, and it actually annihilates X plus Y, because when we apply AB to X plus Y, this is equal to AB applied to X, which we can rewrite as B applied to A applied to X, and then plus A applied to BY. AX is 0 because A is in the annihilator of X, and BY is 0 because B is in the annihilator of Y, so we get 0. This implies that the sum of two torsion elements is a torsion element in any module. Moreover, if R is an element in the ring, and we apply A to Rx, then we can, again, since our action is associative and our ring is commutative, we can rewrite it as R applied to AX, and this is 0 because A belongs to the annihilator of X by assumption. This means that R applied to X belongs to the torsion part. And this proves that the torsion part is actually a submodule. Next, let us discuss torsion-free modules. Let R be a commutative domain. Definition: an R module M is called torsion-free, provided that its torsion part is 0. For example, any free module over a commutative domain is torsion-free. This is clear. So if it's a free module, it's a direct sum of some copies of the ring, and since R is a domain, taking a non-zero element in the ring and multiplying by a non-zero element, we get a non-zero element. Proposition: for any R module M, the quotient of this module by its torsion part is torsion-free. Proof: let M be an element in M such that the corresponding class in the quotient is a torsion element. So there exists a non-zero element A in R such that A applied to the class M plus the torsion part goes into the torsion part. This means that AM belongs to the torsion part. And then there exists a non-zero B in R such that B applied to AM is 0. But since R is a domain, BA is non-zero, and this means that BA applied to M is 0. And this implies that M already belongs to the torsion part of our module, and completes the proof. Let us discuss as a general example Z modules. So consider Z modules which are just abelian groups. Then every finite abelian group is obviously a torsion Z module because every element of a finite abelian group has finite order. So that order divides the number of elements in the group. In general, torsion modules are exactly the periodic abelian groups. So those abelian groups where each element has finite order. The order of the element necessarily belongs to the annihilator of this element, by definition. A good example of such a group is the additive group of rational numbers modulo the additive group of integers. In contrast to this, free abelian groups z to the power n these groups are torsion-free. So for each n, the free abelian group z to the power n is torsion-free. And also the injective abelian group of all rational numbers, the additive group, this is torsion-free, or the additive group of any field of characteristic 0. Also, it's nice to know that if you consider the multiplicative group of all non-zero complex numbers, then the torsion part of this multiplicative group, so this is a periodic subgroup, consists of all roots of unity. Okay, some problems and questions at the end. Question 1, prove that the ring K of x, where K is a field, is noetherian. Question 2, prove directly that any reducible integer is prime. Question 3, prove that the Laurent polynomial ring in one variable over a field is a principal ideal domain. Question 4, prove that the annihilator of an element in an R module is an ideal for commutative R. What happens if R is not commutative? And question 5, prove with all details that a free module over a commutative domain is torsion-free. Thank you very much, and see you next time.